everybody, I would like to welcome you to my next lecture today. Today I will talk about the world energy problem and the amount of energy we need for our industry and our world. If you talk about people about the world energy problem, a lot of them have solutions what we could do, like PV and so on. But many people underestimate the order of magnitude of the world energy problem, and therefore I would like to explain you a little bit more in detail what kind of size this energy problem has. A lot of the options you look at in the newspapers, they work very nicely at small scale, but maybe not at the global scale. If you look at the numbers, you find out you need about 18,000 gigawatts of power. Gigawatt is a unit of the electrical power, the energy per second. So per second we need 18,000 gigajoule, how a physicist would say. If you have problems with the units and things like watt, joule, volt, ampere and so on, I will explain that in my physics lecture at another time. So the global energy consumption is 18,000 gigawatt. How much is that? It's very hard to get a feeling for that, but maybe you know that a nuclear power plant, a typical one, produces a lot of energy, and this is about 1 gigawatt. So if you would go for nuclear energy in the future, you would need about 18,000 nuclear power plants. I will come back to this diagram in more detail later, but what you should remember is about 81% of the energy consumption today is using fossil fuels, which means they are using coal, gas and oil. So this is the majority. This produces the climate change and the greenhouse effects, and that is what we have to get rid of. As I said, I will come back later to that. So we have to stop in future the fossil fuels, and we have to build up a new energy system, and as I will explain you later, I think we have to do it in a renewable way. But before I go to more details about our future energy system, we should try to understand how much energy we really need and how we did it in the past. So let's go back in history to the very beginning. Since when do human beings exist? Well, it's about 200,000 years ago that the modern human developed in Africa, as we know nowadays. They had a similar body like we have today, maybe they had a similar mind, but certainly they had a very different living. What was different at that time? Well, first of all, they had no fossil fuels, no nuclear power. How did they manage with their energy? Well, they had a 100% renewable energy system, and this was working for 200,000 years, so it must be possible to switch to renewables back again. Human beings are different compared to animals, and many people say one of the main features is that we are using the fire, the invention or the use of fire for the first time by human beings. From the point of energy, the use of fire is nothing else as the use of biomass. So we were able to use biomass like wood for cooking, for heating and all kinds of stuff. Then of course people always used solar energy. During the day they had light to see. They used it for heating, but also for drying of fishes or food, for example. At night they used lunar energy. When the moon was shining, they could still see a little bit. Then they used wind power. One use of wind power was sailing boats for transportation, but of course also later windmills. They also used hydro energy, for example in water mills. And finally they also used geothermal energy for hot bath. These thermae, for example, by the Romans were very nice, and there's a lot of literature about it, but certainly also in other countries, like in Japan, it's also very famous. The geothermal energy is used. So this was our long past. Now, 200,000 years later, at some point we started to use coal and then later oil, and later again natural gas. So these fossil fuels came into our business only 170 years ago. So it's not really a long time compared to the life of mankind. And it started with the Industrial Revolution, that we understood how to use fossil fuels to run machines. At the beginning they were running with renewable energies, with wood, with biomass, but then soon people realized that they could use the machines to efficiently bring the coal and the oil out of the ground, and this way the progress was accelerating a lot. So the machines were used to produce fossil fuels, and at the same time the additional fossil fuels were used for other machines in factories and later in trains and then in cars. So what happened in the last 180 years now? Well, I showed you already in my last lecture that the population was rising a lot since the Industrial Revolution and the Green Revolution and today. So the number of people on Earth is rising steeply, which means that of course also the energy demand rises rapidly. If you want to get a number out of that, you have to multiply the number of people we have on the Earth with the average energy demand per capita, per person. And this is shown in the diagram here on the right. So what do you see? You see the years from 1965 until today, and the different curves belong to different countries or continents. So what do you see? The upper curve is the one for the United States. You see the energy demand per capita is the highest there. Then the red curve is the former Soviet Union, so which is basically Russia plus a few other countries today. And you nicely see that the curve is about a factor of 2 below the United States, and it has a drop in the 90s when the change of the communistic government in the Soviet Union changed. There was a drop of industry, and afterwards it slightly recovered. The green curve is a curve for Europe. In Europe we also use about the same as in Russia, and it's about a factor of 2 below the United States. Then the next curve is the blue one, which is the world average, which goes up. So the amount of energy per person goes slightly up. And below you have the curve of China, and you see the curve of China was quite low about 50 years ago. And since then it's rising, and in the last decades it's rising quite a lot, and the last years from today are not on the plot anymore. There's a rise is even steeper. So how to interpret these curves? If you look at the detail wiggles, you can understand it because of political problems like the oil crisis, wars and all this stuff. And the general trend which you learn from this curve is the energy consumption in the developed countries is more or less constant per capita, even though since many decades we tell the people you have to save energy, you have to use less energy, machines become more efficient, but somehow this higher efficiency is compensated by a higher use of people. There are more things being used in our world. We are driving more, we are using computers which we were not using before, and so on. So the standard of living gets higher and the energy use in principle gets higher, but due to the higher efficiency of the machines, this is more or less compensating. So the overall is in the last decades more or less constant in the developed countries. In the less developed countries, like in China some decades ago, energy use was very little, and since then these countries want to have a similar standard of living, and therefore the energy demand per capita rises there. The same is true for India, for example, and if you would have a diagram on Africa, you would find out that there the energy consumption is even much less. So for example, in the US, you have this on the scale about 300 gigajoules per year per person. If you transform this gigajoules per year into something per second, you find out that for the US you have about 9.9 kilowatts per person. In Germany, for example, you have about 5.5 kilowatts per person, and in Africa only 0.9 kilowatts per person. And this, of course, rises rapidly. To give you a much better feeling about what all these numbers mean, I have the following comparison here. 75 gigajoule per year means 2.5 kilowatt, and this is just about the energy which one boiling device uses. So in other words, if you add all the energies you need in your daily life, the world average person has an energy consumption of 2.5 kilowatt, which means one boiling device boiling all the day. And in Europe we have about 2 boiling devices, and in the US the energy consumption is about 4 of these boiling devices running all day and night. Even here you have to say in addition that these numbers here are partially misleading, because for example the currently large energy usage of China is partially due to the fact that a lot of the industrial production is in China, and these are products which are being used in the Western countries like Europe and the US and other countries. So if you really want to calculate the energy footprint of a certain person in a certain country, in principle you have to add the energy footprint of the imported goods to those numbers of energy which you use in your own country. So the imported goods have to be assigned to the consumer and not to the producer. That is one of the reasons why China has higher numbers than it should have. So what did we find out? We find out that the world average today is about 2.5 kilowatts per person. If you multiply that with the 7.3 billion people we have on the globe, and I have to remind you these numbers are not from 2020, but they are a few years old, but nevertheless it doesn't change any conclusion. So if you multiply 2.5 kilowatts with 7.3 billion people, what you get out is 18,000 gigawatt. So the total amount of energy you need per second is 18,000 gigawatt. And in future, if you do a progression of the statistics where you know how many people we will probably have in the future, and you assume that there's a similar standard of living, you would have something like 25,000 gigawatt in the year 2050. Again, to remind you, we have about 18,000 nuclear power plants which we would need today, and in the year 2050 we would have to have about 25,000 nuclear power plants if we would want to have the energy demand of the whole globe produced by nuclear energy. So if you think about the numbers we have just seen, you understand the following argument. First of all, we said we need to build more capacities because there are more and more people on the globe, and a lot of the people want to have a higher standard of living in future. Therefore, we need to build additional power stations. In addition, we had this 81% of fossil fuel, which we have to replace by renewable or other energies. If you add these two things up, we have to build an awful lot of new power plants and new methods to produce energy. And you can calculate that you have to build something like 1 gigawatt of newly produced power production facilities for every day in the next 35 years. Yeah, if you think about the number, 1 gigawatt is about the size of a nuclear power plant. In Europe you need 20-30 years to build a new one. Now you have to build 1 gigawatt on every day, and that for 35 years long. So this is an unprecedented challenge, and it's not only a challenge because of the amount of power plants and methods we have to build, but especially also because of the speed of it, because if we don't replace fossil fuels in the next decades, it will be too late for the climate. And another message which I have to tell you now already, which comes back again and again in my lecture, is if we have to build so many new future power plants, I think they have to be technically simple and inherently safe, because otherwise we produce more problems than we solve. Yeah? If every day there's one more big power station coming and it produces a lot of problems and it's very complicated, we will not have the manpower to produce it, and it will produce problems in safety if it's not inherently safe. Okay, so let's look again at the numbers here. The plot is from 2014, but it's more or less still valid. It's changing anyway all the time, so whatever you write down in the book or in the video is not up to date anymore a year later. But the basic features are still valid. So we have in total about 18,000 gigawatts, and about 14% of that is renewables. And these renewables in this plot here are mainly biofuels. So it's wood for cooking and all this stuff. So it's not necessarily renewables in the sense of a modern system. 81% is coal and oil and natural gas, I told you already, and it's about 5% of the primary energy, which is nuclear energy. There are people which debate about these kind of diagrams, which is correct in a sense, because these numbers are not as simple as they appear here. Every primary energy source has a certain efficiency. So if you want to produce, for example, electricity from coal or from nuclear power, the efficiency is typically 30 to 50%, which means that 30% is only converted for useful electricity in a coal power plant, and the rest is thrown away. The same is true for nuclear energy. And actually, if I say 5% of the number is nuclear energy here, I include the waste heat production. And effectively, if you look about the numbers in more detail, you find out that at the moment we have about 280 gigawatt nuclear power stations on the globe, which correspond to about 280 nuclear power plants, and they produce only a fraction of 1.5% of the electricity, if you count only the electricity, and the total of this 18,000 gigawatts. So in this respect, nuclear power is still negligible on the global scale, and the 5% appear here to have it a bit looking a bit better comparing to the other fuels, which also have a low efficiency in producing electricity. But what kind of efficiency you assign to a certain primary energy source is very depending on what you use it for. If you, for example, produce synthetic fuels out of electricity, you also have a very low efficiency. But if you have a battery car and you use electricity, you have a much higher efficiency as if you use oil or petrol in a car. So depending on the application, this efficiency have a wide range on variation, and therefore it's very hard to compare them very precisely, but these approximate numbers you should still keep in mind, because they give you most of the truth. Another example to the end, if you have, for example, a wind power station, then the efficiency is very high, and all the power which comes out of the wind power station is basically also used as electricity. So to the end of this lecture about the general energy consumption of the world, I would like to show you this diagram here. It shows you for what we use this primary energy. So you see that about 21% is used for residential use, so people living at home running their TVs and their washing machines. We have about 25% for transport, 33% for industry, and the rest is for other things, and about 10% is lost on the way from the primary source to the end user. So it's about, very roughly, it's about 1/3 for transport, 1/3 for industry, and 1/3 for residential use. So this you should keep in mind. And in my next lecture, I will explain you the different methods we have, starting from nuclear energy and fossil fuels and renewable energies. Thank you, and I hope to see you again next time.